It's okay. I have no idea. Neon front. Okay. No, maybe like this. Does this work?
Yeah, that works.
Okay. Yeah. So, thank you very much. Thanks a lot for the invitation. And there's Alex. And not only for the invitation to participate in this conference, but also for organizing the whole event and for allowing me to be here. It's been a great pleasure. So I would like to talk about expansion or higher dimensional expansion and overlap properties of equivariant maps. Which is, so everything I'm going to say is joint work with Christoph Hussar, who's also here. And it's an ongoing project that I like a lot, even though we don't really have any, maybe the dream applications I have in mind, we can't prove any of them maybe yet. But okay, so let me maybe start. So I want to, essentially for those of you who know what Gromov's topological overlap theorem is, I want to, and related things, I want to talk about an analog for equivariant maps. But let me start with something maybe more classical, which is the Ghulam theorem, which is a fundamental result in topology and also has many beautiful applications in combinatorics. And there are many equivalent versions, but let me state the following. So if you have a map from the d-dimensional sphere to R to the d, you want to say that there are always two antipodal points that will be mapped on top of each other. And I will slightly prefer the following equivariant version. So the group Z2 acts just by taking the minus sign both on the sphere and on R to the d. And on R to the d, there is a unique fixed point, which is the origin. So now I want to have a map that preserves this symmetry. And I say that every such map has a 0. In fact, of course, 2, because it's equivariant. Actually, it has at least 2 times an odd number. So this is something that hopefully everybody has seen. There are many different versions of strengthenings. Yeah, if you know how to turn this off, this would be amazing. Has a 0, so has a map. Okay. So what do I mean? I.e., there exists, let's say, P in S to the d with the property that f of p is equal to 0. Really, the distinguished origin in R to the d. I think of this as a vector space with a distinguished origin, which is the fixed point of the antipodality. Is it clear what I mean? Okay. So there are many generalizations. E.g., the following, which I'm actually not exactly sure whose theorem this is. I believe it's Walker, but it might also be Dold, so I don't know exactly. But for instance, here's a strengthening. Suppose X is a d-dimensional complex with a free Z2 action. So you have a symmetry that doesn't have any fixed points. And it has trivial homology with, let's say, F2 coefficients in dimensions less than d. So the sphere is an example of such a thing.
Equal 0.
Sorry. Equal 0. Trivial homology in low dimensions. Thank you very much. Then the same conclusion holds. Okay, it just means that you have a symmetry on your space that maps any given point to some other point. Norm-mapped is kind of mapped to itself, and if you apply the symmetry twice, you get the identity. Like the antipodal map here, but you can think of, I will come up with, I will mention some examples in a while. Okay, so, I mean, this is certainly not the most general version of such a theorem, but it's sort of maybe the model that I want to keep in mind. As I said, there are also many generalizations to other kinds of group actions. I will maybe say a bit more about that later. Yeah, no fixed points. Okay, now I want, so what I meant, one way of explaining this title is that I'm interested in quantitative versions of this. But maybe before I sort of come to those quantitative versions, let me motivate why I'm interested in such quantitative versions. So let me mention maybe some applications of Bosso-Ghulam. So there are legion. There is a beautiful book by Jiří Matošek that is devoted entirely to this topic. Let me just mention a very simple one, which is embeddability. Okay, so which is maybe combinatorial / geometric. So suppose you're interested in the question whether a given graph is planar, can be drawn in the plane without crossings, or more generally, suppose you're interested in whether a given, let's say, k-dimensional simplicial complex embeds in R to the 2k. What, I think you use SX or something, or complex? You had a nice short... HDX, high dimension expander. No, okay. Okay, I never know. I can never converge on a good abbreviation of simulation. Nah, that's different. So I don't want to say that. Not that it matters so much. So the question is, does K embed in R to the D? But specifically, I'm going to be interested in the sort of critical case where the target dimension is twice the dimension. Okay, so how can you, there's a well-known trick, or different versions of a well-known trick that relate this kind of question to this kind of question. What you can form, okay, so for technical reasons, there are two versions. One is the so-called deleted product, and there's one that is called the deleted join. Okay, so I want to talk about the deleted join of my complex. What is that? So first I need the notion of what a join of two simplicial complexes is, which maybe, who hasn't seen this? Maybe raise your hand. Okay, so the geometric picture is, if you have two complexes K and L, then you want to form a new simplicial complex whose simplices are of the form sigma join tau, abstractly speaking, where sigma is a simplex here and tau is a simplex here. And now you can think of this in two ways. You can either think of it abstractly speaking in terms of set systems, in which case this is just the disjoint union of two finite sets. So you realize these on formally disjoint vertex sets, and then the join here is just the disjoint union of the vertices of this one and the vertices of this one. Or geometrically speaking, you can imagine that each of the simplices here lives in some affine subspace, and each of the simplices in the other complex lives in a skew affine subspace. If you go to high enough dimensions, you can always realize this. And then you can take the geometric join. And you just do this for all possible pairs. So if you take the deleted join, you take two copies of the same complex on their on two copies of the vertex set, and you let me just say the simplices are of the form sigma star tau, where sigma and tau are simplices of K and are vertex disjoint. Okay, so that's the deleted join. So let's do a tiny example, the only one I can really draw. Let's suppose this is K. It's just a zero-dimensional simplicial complex. It's just a set of three vertices, 1, 2, 3. And here's another copy of K, right? And now the deleted join is you join any pair of simplices that are originally disjoint, so that have distinct labels. So you get K33 minus a matching, or in other words, you get a 6-cycle. So this is, let's say, this is the discrete complex, zero-dimensional complex, and this is the deleted join.
Can you identify the homotopy type of that for a given K?
For a given K, I don't know.
I mean, the join, we know the homotopy type of that is.
Yes.
We know what its homotopy type is. It's the snatch product with itself suspended once.
Right. So I don't have, in general, I think, in full generality, I think it's quite messy.
How does it relate to the deleted product then?
So the deleted product sits in here kind of as a middle slice. So you can always think of, as I said before, you can imagine that you realize, you take some geometric realization of one complex in, say, some sufficiently high Rn times, say, last coordinate 1. And you take a realization of the other complex in here. Then you get the join, and the deleted product, or the product, is just a slice with a 0 level. Okay, so if you have this, so what the key observation is that if you have a map from K, not necessarily embedding, to R to the 2K, then you get an equivariant map also into R to the 2K plus 1. How do you do it? Well, okay, pictorially, every element of the join can be written as a convex combination of some point in K and some point in L. And what you do is you kind of do exactly this picture. Let me just do it pictorially. You take you take a copy of your image in, let's say, R to the 2K plus 1 at the last coordinate 1 level. You take kind of a mirror image down below, and then so you have f of formal combination would be of the form 1 minus t times x plus t times y. This would be equal to the convex combination 1 minus t times f of x 1 minus t times f of y 1. So you kind of take, if this is minus f of y, comma minus 1, and this is f of x, and then kind of you move along this segment where you have to do. Yeah, sorry, this is a minus. And the observation is simply that sort of the zeros, or the, okay, let's say, self-intersections of f or between two disjoint simplices, images of disjoint simplices, correspond exactly to the zeros of f. Because if you have this kind of convex combination, in order to get a 0, you see that t has to be 1/2 for the last coordinates 1 and minus 1 to be equal. And then that means exactly that f of x and f of y have to be equal, and conversely. And moreover, this map is equivariant.
Why are you talking about self-intersections?
Right. So because I'm interested in, I wanted to ask, do I have an embedding? An embedding would not have self-intersections. So if I have an embedding, in particular, if this map is an embedding, I get an equivariant map that doesn't have zeros. So if I can prove if I can look at the deleted join and I can show it sufficiently complicated topologically, sufficiently connected, for instance, then I can prove that I cannot have an embedding. And an example is, it's a small exercise. If you start with, say, K33, and you take the deleted join, it turns out that this is just, okay, there's a little lemma which says that if you have the join of two complexes and the deleted join operation, they commute. Okay, so if you apply this here, you have that this is a 6 cycle. So this is a copy of S1. And, okay, let's say homomorphic to. And each of these factors here, the deleted join is a copy of S1. So you have S1 join S1, which is S3, which does not allow an equivariant map into R3 minus 0 by the Bosse-Ghulam theorem. So therefore, K33, as we know, does not embed in the plane. Okay, so this is a rather typical example. Oops. Sorry, this will take a moment. My apologies. Yes.
I just have a small question. So usually people don't look at the deleted join when they study, classically, they usually take the deleted product.
Right.
But then they're looking at maps to S2K minus 1 in your situation,
Right.
Equivariant maps,
Right.
So is there any more or any less information?
So the deleted product obstruction gives more information. The main reason why people like to work with deleted joins is because for computing things by hand, they're often easier to work with. Like in this particular example, it takes some work to analyze what the deleted product of K33 is. It's a surface. You can do it, but it's kind of non-trivial, whereas this is really nice and sweet. And there are many other applications in combinatorics where the join is simply easier to work with. But the deleted product obstruction is stronger.
Sorry, I know I should have known the answer when I forgot it. Is this really a topological property? So does it depend on the realization? On the choice?
You mean the join? Or?
No, the deleted join.
The deleted join depends on the specific triangulation. Okay. Yeah, this is
It's not a property of the space.
it's definitely not a property of, it's definitely not a homotopy invariant. It's, okay, so in the twofold case, you can also define the deleted product. Okay, so for the deleted product, I know that the combinatorial deleted product, which is an analog of this, will be an equivariant homotopy, an equivariant deformation retract of the topological deleted product. But this works only if you take two factors, and in higher multiplicities it fails. I'm not sure offhand what the situation is for.
In the case of simply connected manifolds and you use the deleted product, it's a homotopy invariant, at least unequivariant. That's
Right, but this is only for many. It's definitely not true,
not true for
if you don't have manifolds. Anyway, so the question I want to ask is there a quantitative versions of Bosse-Ghulam? And there are sort of different quantitative versions of Bosse-Ghulam. So for instance, there are versions of the kind where you have maybe a higher dimensional space here. And then you want to guarantee not only that the pre-image is non-empty, but maybe you want to guarantee that it is high dimension and so forth. Here, I want to consider a slightly different version of quantitative, where I will still consider a d-dimensional complex. So the pre-images generically will be zero-dimensional, and I just want to say something of the form, if X is maybe not only homologically trivial in dimensions less than d, but sort of quantitatively so, can I force many zeros? Okay, and to avoid the suspense, this is true, but I need to maybe okay. Now I have to decide on the order in which I want to do this. So let me briefly talk about expansion, co-boundary expansion. Which, I mean, is sort of one of the centerpieces of this program, but let me repeat it anyway. So I have my finite simplicial complex X, and I assume I will consider homology with F2 coefficients throughout. So chains and cochains are just subsets of collections of simplices of certain dimensions. And now I want to assume that I have, as for instance Irita has also already done, I assume that we have a weight function on simplices. And I'll assume that this defines a probability distribution on simplices of each dimension. And I don't really assume much beyond that. And then I want to say, then I have a notion of a weighted Hamming norm. On I-dimensional chains or cochains, right? So I can identify each cochain with a 0, 1 vector indexed by the I-dimensional faces, and I can simply look at the weighted Hamming norm of such 0, 1 vectors, where each coordinate is given its corresponding weight. And then I say that X has co-boundary expansion, let's say eta in dimension I, if the following holds, if for every I-dimensional I-1 dimensional cochain with F2 coefficients, the weighted norm of its co-boundary is at least eta times the relevant comparison quantity, which is the weighted norm of, if you will, the cohomology class given by this, which is just the minimum distance to any coboundary. Okay, so this is this gives us a quantitative version of talking about homological connectivity or acyclicity, at least under some assumptions. For instance, if all the weights are non-zero, then expansion greater 0 in dimension I is equivalent to h I minus 1 of x is equal to 0. But it's a more quantitative version, just like graph expansion or one-dimensional expansion is a more quantitative version of connectivity. And so here's a theorem, which is a version of a quantitative Ghulam theorem. So let's suppose X is a finite d-dimensional simplicial complex. Suppose it's an expander, or it has, let's say, co-boundary expansion at least eta I in dimension I ranging from 1 up to d minus 1, which is a quantitative version of this condition. And there's a technical thing. And I have a free Z2 action on my space. That's the whole point. There's one more condition, which is that, so I want to look at this Hamming norm. I also have a symmetry on my space. So I want to assume that the Hamming norm preserves the symmetry. Let's say that is symmetric. Then
That's guaranteed by choosing the weights equivariant.
yeah, exactly. You just choose actually. I mean, actually, you could do even more general norms, but let's just choose weights on each orbit. Each simplices in each orbit have the same weight, and then how do I want to say this? So let me say this is the number of simplices so I look at the collection of these simplices whose image hits the origin. This, I think of this as a cochain. I look at its norm, and this is at least the product of the expansions over 2 to the d. So it's a universal and
Eta I is the expansion
yeah, so I think of dimensional expansion. So for me, edge expansion is one-dimensional expansion from 0 to 1. Eta 2 measures from the 1 skeleton to the 2 skeleton, and so forth.
Here you don't measure the spectral norm.
This has nothing, or I wish we could capture this in terms of spectral norm. This is a different kind of measure that we don't, actually we know that it's not captured by the spectral properties of our complex, unfortunately.
How can you wish it's not true?
Well, I still wish it were true, or some version of it were true, because I think it's fair to say that we understand spectral properties much better than we understand co-boundary expansion. But I don't know how to prove such a theorem using only spectral properties. Well, okay, no. So I don't know that a version of this theorem is not true in terms of some variant of spectral properties. In fact, if I have time at the end, I'll maybe mumble a little bit about this. But I definitely know that spectral properties are not enough to bound the co-boundary expansion. Okay, so just for comparison, so this is what I call an equivariant topological overlap theorem. And you can think of it as a baby version of a result of Gromov that I talked about at length at the opening conference, and that many of you have seen, but let me maybe just, for comparison, state it. Mm-hmm. Please go ahead. I will.
It could be true that for a complex that has only spectral expansion, the conclusion is still true.
I don't know, offhand, I don't know a counterexample.
So the counterexamples that you guys constructed for separating.
Yeah. So these definitely still have this. These have the counterexamples we specifically constructed. They even have the non-equivariant topological overlap property, which is harder to prove. So I don't know. But I simply have no idea how to connect spectral property. Or
It's the same problem that spectral expansion are not co-boundary expansion. They are at most you can expel them what's called now systolic.
No, but he's saying that here he does expect, he could expect the same conclusion.
But yeah,
Yeah.
that's exactly what we have.
They are not co-boundary expanders.
They're not
They're not
boundary
co-boundary.
expanders,
Yeah.
but they do give this conclusion.
But they are spectral, but not combined.
Right, so I don't want to state Gromov's theorem completely formally, but so Gromov has a very similar sounding assumption, just you have a d-dimensional expander, and then the conclusion is that for any f from x to r to the d, there is a point, some point, whose preimage hits also a fraction, but the fraction is, so it's not so unsimilar, but the fraction is at least something like the product of the expansion factors over d plus 1 factorial. So you definitely get a worse bound, and in general here you cannot improve this bound. No, that's of course nonsense. Well, okay, in 2 dimensions you cannot improve this or something very similar to this. Even here we don't know the exact answer. And as Alex pointed out, this holds even if, so you can weaken the assumption here to something that is called co-systolic expansion, where you allow for some non-trivial homology, but you want that all the sort of non-trivial co-cycles are large. Let me just mention that this fails for co-systolic expansion. So so you cannot prove this theorem if you, in the hypothesis, replace co-boundary expansion by co-systolic expansion.
You cannot prove it, or it's not true?
This is simply not true for a very stupid reason. You might be able to come. So the example is very silly. Look at 2 copies of the complete graph Kn. And you flip from one, the action is simply you go from this copy to this copy. You can certainly map this in a stupid way to R1 without hitting 0. This is just saying that the obvious attempt to generalize this to co-systolic fails. I'm not sure what happens if, for instance, you have some equivariant co-systolic condition or something like this. But at least the straightforward generalization fails.
Explain why this is a baby version of that.
Why this is a baby version of that?
What did you say? Whose baby version?
So this is a baby, okay, so this is a baby version. I call this a baby version. I think formally I don't see any way of, at least with the constants relating one to the, I mean.
Well, because of the Z2 action, what's the
Right, so okay, so here clearly if you don't care about the constant, then, you know, an arbitrary map, an equivariant map is in particular map, so you know that some point has a big preimage. But the thing is, I don't know how to deduce from this that the heavily covered preimage has to be 0. Just if you just take this theorem as a black box. This is some point with some constant, and this is 0 with another constant.
But there's one of the other equivalent formulations of force of Ghulam doesn't, starts with unequivariant maps.
Right.
And it says there is a point whose preimage is a pair of it.
Right.
Is there sort of an analog in your quantitative theorem of that other version of force of Ghulam? We're not.
There should be, yeah. I mean, you can. I think you can just do the translation that you do, where you start. You still need a Z2 action on your space, on the domain, and then you can simply, if you have an arbitrary map, you can simply turn it into an equivariant map by taking the difference between f of x and f of minus x, and then it becomes equivariant, and then I think you get the same kind of behavior. So there would be a version where you're not interested in 0, but just in some point that is now covered by the preimages of many antipodal pairs. But also that version, I don't know how to deduce from this theorem because you want pairs.
But the two versions are equivalent.
What? No, the Borsuk-Ulam versions are equivalent. I'm saying I don't know how to I call this a baby version because the proof is much simpler, but I don't know how to deduce it from the non-baby version, is what I'm saying. So rather, we just do the proof and it becomes much easier. Yeah, so good question. So if you, for instance, have a, I don't know it for, okay, we don't have a version for completely general groups, but for instance, there's a version with a ZP action. And then instead of 1 over 2 to the d, you get something like the quotient becomes, here you get the same, but then here you get something like 2 to the d over 2 rounded up. And then you have p to the d over 2 rounded down. Which for p, so roughly 2, so in the denominator, sorry, numerator, denominator is replaced, instead of 2 to the d, you have 2 to the d over 2 times p to the d over 2. I don't know whether this is sharp, but this is a version that we have. I should also say that this is sharp in general, so you cannot. Yes, z2 to z2 to the n. I don't know now as a symmetry group. I don't know. So we haven't looked at what happens if you have powers of cyclic groups. I would imagine that some of it can be adapted, but I don't know. Okay. Oops. I'm completely. Yes.
So etas depend on your coefficient.
These etas, they are a property of a complex with respect to a fixed system of coefficients, in my case F2, which is, so there's a symmetry group, which is Z2, and there is a, okay. So, you're right.
Weights have to be respect symmetry.
The weights have to okay, so I didn't state the ZP action version completely precisely. So you need the weights to have more, to respect more symmetries, and Eran is of course also right that if I work with a ZP action, then the natural field of coefficients to consider is ZP, and you would just rephrase everything that is stated here with ZP coefficients in the homology instead of Z2 coefficients, and then you get this theorem. Okay, I completely lost track of time. Who's in charge?
You know where you are.
I mean, I know where I am.
3 complements out of 4.
Yeah. 13. Okay, that's of course much less than what I was hoping for. Okay, let me see. Okay, so that's not enough to. Okay, let me tell you a question. Let me do it this way. Let me try to give some context. And if time permits, at the very end, I will maybe sketch a proof. But for now, let me rather, instead of giving the proof, let me give some context. Or let me start with the question. Suppose K and L are expanders. So let's say this has dimension K, and this has dimension L. Co-boundary expanders in dimension less than their own dimension. Is it true that the join also is a co-boundary expander up to dimension K? So it has dimension K plus L plus 1. Is it a co-boundary expander?
Is the link the join of the links?
Is the link the link of a face, you mean? Yeah. So, well, rather it's, yes. So this is, so you can, spectrally this is not a problem. There's even, you can even Okay, I'll say something about that in a minute. But here I really mean over F2.
Yeah,
Okay, let me mention that. So the qualitative statement is true. So this is a classic fact that so if you have complexes K and L whose homology up to say the top vanishes, then the homology of the join also vanishes up to the top dimension. You can be much more precise, so that you can specifically write down the homology groups of the join in terms of the two factors. But I want a quantitative version of this, and we don't know. So just something that only depends on the expansion factors here. If it were true, you would immediately get interesting applications. So you would, for instance, immediately get a quantitative non-embeddability result for expander complexes, something that Alex and others have been asking for long.
They won't be bounded degree.
No, but that doesn't matter. This is not bounded degree. But what I'm saying is, suppose something like this is true, let's say for K and L bounded degree expanders, or any co-boundary expander.
Yeah, but even if K and L are bounded,
the join is not bounded degree, but it could still be a co-boundary expander. And if it is, you would get, if true, no, it won't construct. No, it will not. Okay, so it would be some weird construction of things that have co-boundary expansion, but as Alex points out, they are not bounded degrees, so they have these kind of very unbalanced degree distributions. So from that point of view, they're maybe not so interesting.
I want to stress that as of now, we don't have any even suggestion for a zigzag construction of the high-dimensional.
Right.
Like there is
No.
elementary, even conjecturally.
Right. But this is a much simpler construction. It's one of the simplest construction on simplicial complexes, and I don't know the answer, and it's embarrassing. But if true, it would mean that every map from an expander, let's say a d-dimensional expander, to R to the D, R to the 2D, has quadratically many crossings. Okay, if you had such an expander, okay, let's assume it's also locally sparse. That's a technique. But let's sort of permit that. Then if you have an expander K, then its join with itself by this would be an expander. But then it's very easy to see that the passage from the join to the deleted join, if you have some local sparsity condition in your complex, deletes a little o of 1 fraction of the faces in each dimension, which means that in terms of expansion properties, it doesn't affect the argument at all. Which means that the deleted join would still be an expander, at least maybe apart from some very small cochains that don't matter. So the deleted join would still have suitable expansion properties, and then you could apply this theorem to the deleted join, and you would get this kind of result simply by plugging this in.
By the way, said that for the join, not the deleted join, you know that the answer is positive.
No, I know that the homology is 0.
You don't need it. You can apply also common. Because the C action is not really important, right?
I don't know how you get the. So I mean, with
if K star K has many, there is a point which is.
no, but this doesn't measure. This would measure zeros of the map, but you wouldn't necessarily. Let's see. It's probably true what you're saying.
Why is this a hard problem? I mean, you have an explicit model for the complex, right?
Yeah.
So
It's
you
because we
write
have.
down the co-boundary operator.
Yeah, but it's somehow we have no techniques for proving co-boundary expansion. So let me mention some partial things. So using this local to global machinery that we have been hearing about a lot, one can, for instance, show, at least in some cases that Pascal has worked out, that, for instance, the join has expansion properties on small cochains, things like this, for those who know. But we don't know how to deal with large cochains. The problem is simply that even if I give you a concrete but fairly reasonably large complex, even if you have the co-boundary operator, you're asking some kind of computationally hard problem. And we don't have any good sort of general purpose approximation for this. Let me also mention that
if you take K star L, what are the links of places that there are?
So you can also express them as joins of links.
So maybe you can kind of use some kind of an induction on the dimension and use the results of Shai and Kali.
Right, exactly. That's what I meant with local to global arguments. So you get expansion on small cochains. I don't know I don't know, Pascal, do you remember? Okay. But just some pretty...
If you have expanded small cochain, that's enough to get normal.
No, because expansion on small cochains is not enough. Because you need...
One dimension less.
No, but you see, it's not enough. You like, I mean, as this stupid example that I told you.
No, but don't think about that. Go back to Gromov.
Yes. Okay.
If you have expansion in small cochain, then you have the Gromov conclusion for it.
So you are saying you look at
One dimension.
No, but expansion on small cochains is not enough. You need co-systolic expansion or something like this. I don't see how you... No, you need, for the proof of Gromov's theorem that I know, you need you need some combination. You need an isoperimetric inequality on all cochains, but plus you allow non-trivial co-cycles, but these have to be large.
But here you don't have at all, because you start with the co-boundary expander, then the HI vanish anyway.
Yeah, that's fine, but you don't know that you have a good isoperimetric inequality on large cochains. So it's still possible.
Except for dimension one.
Yeah, but I don't see. Okay, I don't see how. I mean, maybe it's possible to fix it, but I don't immediately see how to overcome this difficulty. Let me. Okay, so what? Like 2 minutes, 3 minutes, -7, 2.5. Okay. Okay, let me just mention there was a naive hope that started me on this question. But so the initial naive hope was that if K and L are optimal expanders, so what do I mean by optimal expansion? One, so the examples to keep in mind are things like skeleta of simplices, so complete complexes, where the expansion factors are 1. This essentially holds true in the spectral case, but unfortunately, okay, so I just wanted to mention it because it still saddens me. If this were true, it would actually solve a number of long-standing problems concerning crossing numbers of graphs and so forth, simply by plugging these two things in. So the application would, there are several long-standing open problems about crossing numbers of graphs. For instance, what is the crossing number of the complete bipartite graph? What is the minimum number of crossings of KMN? The conjecture is that the best thing to do is to distribute the points in each color class roughly evenly on each of the axes, and then draw the graph like this. No, this was asked in 1944. It was announced in 52, in the 1950s, and then it was found the proof is fundamentally flawed. Exactly. So this was asked by Turan. And the conjecture is that the number of crossings should be roughly m squared times n squared over 16, for instance. Okay, you just count this. And this would give it up. It would give the exact constant if this naive hope were true, which is why I was very excited about it and forced Christoph to try and prove it for about a year, but it's false. But anyway, I still have some hope. So if you had expansion 1 here in each dimension, then you simply get a factor of 1 over 2 to the dimension, which if you look at the deleted join of KMN, we know it's the join of each of the factors. So it's essentially, it has this number of top dimensional faces, m squared times n squared. This would give that the number of simplices under the equivariant map from the deleted join to R3 is 1 over 8 of everything. But then you count every sort of, because of the symmetry, you have to divide by another factor of 2. So it would give the exact answer. It would give the exact answer for the complete graph. It would give the exact answer for many related questions. But unfortunately, this is just false. The smallest example is if you look at the join of 3 discrete point sets. So a tripartite, complete tripartite, 2-dimensional complex. This has 2-dimensional expansion. So from 1 to 2, at most 3 over 4, to our great disappointment. And even, maybe I should say this, so we know it's at least 3 over 5. This follows by difference arguments. For instance, Dotter and Kale have an argument that shows this. We don't even know what the expansion is for this extremely concrete complex, which is an embarrassment. But anyway, yeah, so the hope is that despite the failure of this, that this has maybe still some bearing on these kind of conjectures, but as of this moment, I don't know. So I'll stop here.